Hi to everyone, I'm Sara Pérez-Vieites from Universidad Carlos III de Madrid, and I'm going to present a nested hybrid filter for parameter estimation and state tracking in homogeneous multiscale models. So we aim at tracking homogeneous multiscale systems that can be found in many fields of science, such as biology, physics, material science, or chemistry, for example. And the goal of this work is to estimate the time evolution of a system that is governed by processes with different time scales that may be described by diverse laws or different equations. And also they can have cross dependencies among them. So if we think about the simplest case of a multiscale system, it would be the one with static parameters and dynamic state variables. And for this particular case, we can find theoretically guaranteed solutions such as sequential Monte Carlo square or particle Markov chain Monte Carlo that aim at computing the joint posterior probability distribution of all the unknown variables and parameters. But they are batch techniques, so they are not well suited for long sequences of observations. On the other hand, we have nested particle filters that are schemes with two intervened layers of Monte Carlo methods that approximates the same distribution, but in a recursive way. In any case, the computational cost is still prohibitive, so we can use nested hybrid filters that take the idea of the nested particle filters, but introducing Gaussian filtering techniques in the second layer of the algorithm that reduces considerably the computational cost. So the idea of the multi-layer algorithm is based on these nested hybrid filters, using a different layer for the different time scales we have in the system. But first of all, we need to introduce the state space model. We are interested in systems that are described by multidimensional stochastic differential equations such as these two, where t denotes time, x is the slow state variables, and z represents the fast state variables. That means that they work in different time scales. We have also a couple of functions f and g that can be nonlinear functions. We have these non-scale parameters, sigmas, that control the intensity of stochastic perturbations. And we have also V and W that are vectors of independent standard linear processes with dimension of the slow state variables and the fast state variables. As both states work in different time scales, we need to use a macro-micro solver to integrate them. The idea of this macro-micro solver is the use of an Euler integration, but with different integration steps. We have delta z for z and delta x for x, being this one quite bigger than the integration step of z. Then we denote discrete time in two different ways. We have, on the one hand, we have n to denote discrete time in the time scale of the slow state variables, and we have k to denote discrete time in the time scale of the fast variables. We have also here h, that is the ratio between the two time scales, the time steps z needs to take to reach the next time step of x. So we have also this var z that is basically the average of the last 8 steps of z we need for the integration of the next time step of x. Well, this is easier to explain with an example. So for example, here we have z that goes ahead 8 time steps. And thanks to this, we can compute var z, that is the average. And with this average, we can compute the next time step of x. So once the state space model is introduced, I want to talk to you about the model inference and the general methodology of our algorithm. So the main idea is that we aim at approximating the joint posterior probability density function of z, x, and theta, and we use the chain rule to factorize this PDF. Having three different PDFs, we can handle in different layers of computation. So for example, we can compute the posterior of the parameters in the first layer, the posterior of the slow state variables conditional on theta in the second layer, and the posterior of z conditional on the slow states and the parameters in the third layer. So maybe the most difficult thing would be to compute the posterior of theta because we only observe the states x and z. So with this scheme, I'm going to explain how to do it. So in the first layer, we need to compute this that can be written like the product of the likelihood of theta and the posterior PDF of theta at the previous time step. This can be integrated in the second layer as the integral of the likelihood of theta and the slow states multiplied by the joint predicted PDF of the slow states. And we repeat again, computing this likelihood in the third layer as the integral of the likelihood of theta, x, and z multiplied by the predicted PDF of z. If we do a particular implementation of this methodology, we obtain something like this. We have taken an SMC, a sequential Monte Carlo, for the first layer with capital N samples. For each of these samples, we have another SMC in the second layer with capital J samples, and per each of these samples, we have another unscented Kalman filter in the third layer with L plus 1 sigma points. So we would have a complexity of N by J by L plus 1. So I'm going to explain briefly how the steps of this algorithm would be. So first of all, we need to do the jittering step in the first layer. So we move a little bit the parameters with a very small variance in order to avoid degeneracy. Then we do the prediction step of Z and X as I have explained with the macro microsolver. And after this, we can compute easily the likelihood of theta, X, and Z, and then update the sigma points of Z in the third layer. And thanks to the predictive PDF of Z and this likelihood we have already computed, we can compute the likelihood of X and theta. Then we can obtain the weights we need to the resampling for the resampling step in the second layer. Thanks to this likelihood we have computed and the predictive PDF of X, we can compute the likelihood of theta. And with this, we can compute the weights to do the resampling step in the first layer. And we can compute the posterior PDF of theta with this likelihood of theta and the posterior PDF of theta in the previous time step. And finally, with the three posteriors we have already obtained, we can compute the joint posterior of the fast states, the slow states, and the parameters. With this scheme, we have obtained some numerical results for a stochastic two-scale Lorenz 96 model that is described by these stochastic differential equations. And we have some slow state variables again, and some fast state variables again, being the dimension of the fast variables greater than the one of the slow states. And we assume that static parameters H and B are known, while we need to estimate capital F and capital C. We have assessed the results of the experiments in terms of normalized mean square error, and we have obtained an error between 10 to the minus 4 and 10 to the minus 2 for the parameters, the slow state variables and the fast state variables, having a convergence of 5 units of time in the case of the parameters. And we have also plotted the approximate posterior density functions of F, C, one of the slow state variables and one of the fast state variables in the very last time step of the experiments. And we can see that these posterior density functions get close to the true values that are plotted in black. And finally, to conclude, we have introduced a new recursive methodology for tracking the time evolution of multi-scale systems. It's a nested multi-layered structure that allows different computation schemes at its layer. We have explored the use of SMC in both first and the second layer, and the use of an unscented Kalman filter in the third layer. And we have also analyzed a dynamical system of 3 time scales with static parameters, slow dynamic state variables, and fast dynamic state variables, showing the average performance in terms of normalized mean square error. So that's all. Thank you for watching. I hope you have enjoyed. Thanks.